Hi everyone, hope you're doing well. Welcome back to class, such as it is, virtually. Today we're going to start talking about reinforcement learning in the deep learning realm. So we have this wide range of approaches to applying deep learning to make reinforcement learning scalable and effective for more complex problems than we've ever seen before. In this course, and even anywhere until like 10 years ago. So it's really a fast-moving field. If we look at this table here, on this tree, we can see kind of a hierarchy of at least one point of view of the way reinforcement learning algorithms fit together. I think it's a pretty good view, even if it's a bit simple. It's missing some dimensions, but it's a good basis. This figure comes from OpenAI, which is an organization that's contributed a lot to reinforcement learning research in recent years, just like other organizations, universities, and companies like DeepMind have contributed a lot. A lot of this research and advancements not necessarily happening in universities at the moment because there's a lot of exciting applications from reinforcement learning. So that figure comes from here in a really neat page in the middle of really neat documentation website for OpenAI. So OpenAI has an entire kind of set of documents on the algorithms, reinforcement learning, all the field and things that are happening going forward. So I really encourage you to go look through that and use that as your basis to take this course as a jumping off point and explore more on what's happening next in reinforcement learning or using models depending on the task you're faced with. So you'll kind of have to use this because for the final assignment, we've got two environments. So one environment you are familiar with, the maze world that you used in the previous assignment, which seemed to go very well. So you can apply basically the exact same environment again, so you don't have to learn anything new or set it up. Just, I don't know, create a branch or something. And try out using some deep learning algorithms on it. And then we have a new, different environment for you to try out on. This one's a bit more fun. It has kind of two agents that are trying to learn how to play a ball, but it's also a continuous action space. So you're trying to decide when to jump and how high in order to hit the ball at just the right timing. So it's a bit more complex, even though the actions aren't super complicated. There's a whole API for playing that, and there's example code up here on their GitHub to let you kind of start with it. And in the assignment, we have some example code as well on how to use one of the deep learning methods called PPO, which we'll talk about in the next video. It's a policy gradient algorithm, and there's some code for doing that. In the assignment, that's not the algorithm we're asking to use. So we're asking you to implement DQN and A2C, and one other one of your choice. So there's other ones like DDPG or lots of other acronyms that show up on this table here, basically, any of these. And as people have seen, option one for the assignment is just to use the libraries that OpenAI organization has created for you, well, for everyone. They have easy to use implementations of these standard algorithms. And you can use those and run a bunch of them and do experiments on your performance when you've trained them, and that would be your report. Option two would be just to implement a single algorithm, but to do it from scratch and implement basically your own neural network that represents everything, and then have it do the algorithm, which is not much more complicated than the ones you've done for the map assignment in assignment 2, except that now instead of a value function being stored as a lookup table, you've got a neural network. So how does that work? That's what we're going to talk about today. So hopefully that's all useful. Games useful. But yeah, this website's super great. I'm always looking at it as a reference because they also link to all the relevant papers for each type of algorithm once you get there. So you can go to the source and figure out how these things worked. It's a great resource. So what are we talking about here? This overview, the idea is that they've broken down to a couple different types of approaches. So we didn't focus on it too much, but early on I talked about model-free versus model-based RL. And the distinction, right, is whether you know the model of the system, right? So remember, we've got our policy pi that gives us actions we can take in a given state. And it's going to have some parameters, often theta. We have, if we think about our NDP, we've got states, we've got actions, we've got rewards. But the other thing we have is our dynamics function, right? And it's been written various different ways. But that's the transition of states from one state to another when you take an action, right? And so this is what we're calling the model. Right, and so in a model-based system, you know this, you have this one. And a model-free one, you don't know it. Right, so you could think of planning algorithms essentially as ones where P, the model is known, as well as the reward model is known. And you could have an optimization function, you can really just solve it directly, as well as the form of the policy. In RL, we've kind of like dropped some of these things so you don't know them, and then how do you learn in the absence of it. But there is part of reinforcement learning where just the model is known, but all the other parts aren't. So you still have to learn by experience, but part of what you're doing is learning this model. So trying to figure out how the world works and learning patterns of basically how to predict what happens next, right? And you can use a lot of standard supervised ML to kind of learn these models and then apply kind of planning to it. So various things there. In some famous models, you're given the model directly. So if you have a simulator for the game you're playing or of your opponent, that lets you play against yourself or simulate forward. The AlphaZero approach for playing Go and some other games was using that. But in this more interesting realm where all of these things are unknown, you have model-free problems where you don't know P and you don't know R and you have to learn your policy. And within that, there's kind of two major approaches. I don't know if I would call this Q learning, but we would say that they're value function based, right? Methods. So the idea is that you have a value function, you're optimizing your value function. The value function could be QSA, right? Or it could be VS, and you're trying to learn them all of that. And once you have that, then you can learn deduce your policy by running some kind of max or something else. So Q learning that we learned obviously fits in there, and there are versions of deep learning algorithms that use Q learning style learning, and that's the first one we're going to talk about today. It's called DQN. It changed the world not that long ago, 2016, 2015. The other approach, which we've talked about, are policy optimizations. So these are policy gradient approaches, which we've talked about in the lectures. But there are deep versions of those as well, where in this case, you're learning the parameters theta of the policy directly, and you learn something that is like the gradient of that, and then you update it, right? So you're trying to optimize the policy directly. but using a neural network. And there are a lot now, the really cutting edge ongoing things that are happening are finding ways to do both of these things at once. So that's kind of an overview of the state of where things are for deep learning for deep reinforcement learning in terms of how they're breaking down. And there's actually been, new algorithms since this, because I think this figure from the website is actually a couple of years old. But let's go back to the beginning. Where did it start? So it started in the 1970s. I never played with this game, but it existed. I had friends who had it, although it was kind of an old game even then. But obviously, this game itself doesn't have anything to do with it. But the games that came out of it did. I think I probably talked about this in one of the first lecture. So is the Atari, I guess the Atari 2600. It's a video game system, and you put the cartridge in here, this big physical cartridge that had ROM memory on it, that had all these pins, and you stick it directly into this thing, and then you get one game. And the important thing to note here is the joystick. There's just the stick and a button, right? And the stick has 8 directions, and the button only has 2, right? On or off. So that is your action space in these games, right? And the state space is not that big either, because screen resolution is only that many pixels, only that many colors. Multiply those together, it's not that big. You can actually represent all of it in there, and this machine only had 1K of RAM. Yes, that's 1,000 bytes of RAM, if you can imagine. What they look like is these pixelated video games, which you've seen, but they were really the best games people had at that time. The fun part is that since these games are so small, you can create a data set where every single state of the game is represented, and this would literally be state 5 because it's all the pixels in it, and you can still represent it in memory and have this as a downloadable data set. So a prof at University of Alberta did this in 2013. I don't know if he regrets it. He probably doesn't regret it, but it's a big deal. I remember people talking about how it was going to be used and kind of be a long, probably quite a few years of people using this interesting data set and exploring it. And it turned out a few years later, basically, DeepMind created an algorithm that could play the whole thing, or at least learn how to play the whole thing. So it advanced very quickly from when it came out to a few years later saying, oh, here's how you do it. But the data set was essentially every frame. If you had an action, what would happen next? And it's just deterministic. And so you can represent the game state. You could also represent the internal state of the machine in those 1,025 bits of memory, and just use that directly and not use the image, which is interesting. So if we think about how to play this, how to learn how to play this game, we could use 2 different ways. We could use the value function approximation approach that we have some video on, or we can jump in and talk about the deep learning approach. That's what I'm going to do now, and then I'll post up the little discussion as a separate video for the value function approximation approach after. Because the fact that this was used for Q-learning, just like I said, a couple years later in 2015, was the big deal. So there it is. This is the DQN network, the Deep Q-learning network. And the idea was you take one of those input image states, right? So like I had before, state 5, which was an actual world with some little aliens, and they're shooting, and you're here, and you're trying to defend yourself. So the entire image and all the pixels, that's the state. And then we're going to apply, use that as input for a deep neural network, right? The kind of network we're using here is called a CNN, and then you could just call this a DNN, which is fully connected, and they have to connect between them. And so How this works is its own separate, career or course. But the idea is that the image gets taken in and many different patterns are learned from it. So the convolutional neural network applies kind of many different filters and applies filters on the pixels and then scans them across all the pixels and learns lots of different patterns, right? So maybe it's going to learn a pattern which is there's a ground here and you're here. And maybe another pattern is going to be some shape. And these are usually going to be like 5 by 5 pixel patterns. And these could be come out to be edge detectors or detectors for objects or guns or weapons or aliens. It's going to learn that through supervised learning. But what are we training it on? So using the standard approach that people do in supervised learning for neural networks, you have to have a label, right? So you got your X and you got your Y. We've got our data and we've got our labels, right? So this is why it is a type of, in this particular instance, is a type of supervised learning where we've given it a new problem. And the label in our case is the outputs of that crazy joystick. You've just got your 8 directions and 8 directions with the button on its own, and no direction, no button, no input. So that's all the actions you have, and that's the label. So you can say, well, given that this happened, and then they pressed this action on the joystick, was it good or bad? What happened? So we can use that to basically learn a model based on something, right? So that was the first idea, that you can use a neural network to represent turning the state into an action, right? And so what would that be representing, right? You're taking, well, there you go, I just told you. You're taking an action, a state, and you're giving an action, right? So that's actually defining the policy, right? So yes, so if you don't know what deep learning is yet, that means you didn't watch the YouTube lectures. I created a playlist on YouTube with some lectures from my grad course on deep learning, so you can go look at those. And it just has a summary of the core components so that this picture kind of makes sense a bit. The way you're going to be using it, you don't need to have them in detail, but the more you know about it, the better you're going to be able to train them and set them up. So knowledge is power. There's also some other slides, I think, on the website, which you can see, which have all that kind of distilled down into one slide deck. The main idea, then, is using neural networks to basically perform value function approximation and policy function approximation so that we can use this powerful computational structure and algorithm to perform learning for planning. So in a value function approximation we talked about earlier, you come up with a linear set of features or weights or some kind of trick that helps you distill the state space into something more compact. Now we could use this approach of representing the game as a neural network to learn that, right? So one thing you can do when you've trained a network like this is that the representation you get in here, you can use this network as a function to get a kind of encoding of states, right? Once it's seen many different examples of states and actions and outputs, the code that is used here essentially represents a way of turning input states into a representation and its relationship to actions. In supervised learning, the thing you're usually using as your signal is a label, right? So if you're trying to train a neural network to identify cats in pictures, you give it input images, this is what we're doing, and the output image is going to be, is it a cat or not? Or list any animal you think it is. And we tell it what the correct answer is, right? And if it gives you a prediction and the prediction is wrong, then you produce an error, right? You give that's what we call the loss function. So the loss function that will give you an accuracy for saying cat or not cat, right? Got your image of your cat, right? Very bad cat. And then we've got some neural network, and then it's going to have a bunch of categories, so to say. And if it gets it right, then it gets a positive, and if it gets it wrong, then it gets a negative, right? And the negative or positive scale can actually be numerical, and depending on how far away it is, if the number you're predicting is more of a distance or a continuous number. But essentially, you can say whether that prediction was good or not. And then you use that good or not when you're feeding backwards to train the network to give you some weighting on the derivatives. So you compute the derivatives of all these weights, and you have a positive or negative weighting on them, and then all of the updates to the network to slightly improve it are influenced by whether you got that right or not. So the same thing's going to happen in reinforcement learning, but instead of accuracy as our loss function, we're going to have something where we are saying, well, how close were you to predicting what's happening next, right? How close were you predicting the value of the outcome, right? So when you take an action and you predict a certain reward, or you think it's the best action, and then we figure out after you took it that it was a very bad action because you had a negative reward, we can use that now to compute a loss function that will train it not to identify and just copy the action that you took, but to take the action that maximizes the reward, right? So it's just a matter of turning the reward signal into something that we can use as a supervised training signal. That's the main idea. So in the DQN framework, this is all for the DQN initial paper that I was talking about there, they do it by creating two networks. So they have one network to represent the Q function, the value function. And so the parameters there represent states and actions, and it's trying to predict the value. And the output that's going to come is something that's going to be the value. Function looks like for DQN. Right, so now instead of, like I said, this classification accuracy for whatever supervised problem you're doing, we have this network that represents the input states and coming into the output states, and we're trying to train one that is consistent with a certain policy. And so we're going to maintain two different networks. So they've got the Q network, which is the one using theta here. And then going to have a target network, which is going to use theta minus, and that's going to be here, right? And so if we look at this as we kind of can remember, right, what are we seeing here? We're seeing our Q prime minus Q. If you remember, that's the TD error, right? We've actually got, the current reward we've encountered, the discount for going into the next state, our assumed best action that we would take in the next state, assuming we know we're given what the next state is, because we see where we've arrived. So what we would have done if you told us what the next state was, and then we've got our value that we assumed we were going to have when we got to the state initially and took the action before we saw the outcome, right? So it's this temporal difference that we've talked about and used over many algorithms, right? And it's part of this essence of learning from your experience and your change in knowledge, right? Because you've got the model as you came into it, you've got the model with a little extra piece of knowledge that you now know what the next state is, but what would you do? And how much is it off, right? So, because now you also integrate it with the actual reward you received. And so if this is off by some amount, then you want to adjust it so that the reward you expect to get is closer to accurate, right? And if you can do that, then when you're maximizing the Q function, you would take the best action, the actual best action, because your estimate of the rewards would be correct, right? So that's what everything feeds back to. So in order to do that, we're going to have two different networks that basically track this differential one and the true one. And so the target network, which is this one, that's very bad writing, sorry. The target network doesn't change as often, right? So we only update it once we've seen a kind of number of experiences. And they did this in order to create stability. They tried not doing it initially, and it ended up being that a single network just kind of careens around up and down, chasing its own tail in a way. So having it have two different aspects to stabilize each other seems to be an important aspect for deep learning with these complex models. Another thing that they did is they stored, they introduced this concept called experience replay, where you store all the experiences you have, right? The SARS or SARS pairs, tuples that we've experienced through our training. And you keep them as a series of experiences. And then when you're trying to train the network, you go back and sample experiences randomly from this database and keep training. So this seems like a bad idea from a reinforcement learning point of view. But neural networks are so big, have so many weights, they're essentially a hugely under-constrained system. So you can fit anything you want, right? You need a lot of data in order to get a real signal, a pattern in here. And every time you go back and update the network with its backpropagation using its gradients, all the weights just move a little bit, right? And so going back into the past and sampling many things that happened and re-experiencing them over and over again lets it converge on things, even though you're really seeing the same things multiple times. If you think about it for yourself when you're like trying to learn a sport or a game or something, you might think back over how you did a thing and what the right thing to do was. Every time you think it over, you kind of learn a little bit better because maybe you see some other aspect of it, right? So replaying it in your mind is not a bad idea, actually. And that's exactly what they do with this experience replay idea. So not all deep reinforcement learning algorithms use that, but DQN did. And it was essential for getting this initial result, which was basically building a kind of straight up, almost obvious neural network for representing a policy, but getting it to work on this crazy data set, which is all these video games. And they did it. It really worked. So I don't know if I can play this. Oh, I can't because it's PDF now. So if you go to that URL, sorry, there we go. Oh, it's not good. Here we go, hopefully you can see it now. The idea with this one, you can go look up the URL on yourself, but the main idea is at the beginning, it doesn't know how to play the game, right? And so it's got a network like that that's really just trying to learn the controls of this game. So this game has a very simple set of controls, right? Which is it just controls the location of this paddle at the bottom, and you have to be in the right place at the right time in order to bounce the ball. And then it goes up and hits it. And the goal, obviously, is to get rid of all these blocks, right? And so after they trained it a bunch of times, you could see that it got better and better. Oh, I have to stop clicking, sorry. After only kind of 600 episodes of playing this and doing this replay and experience things, it was able to work out that the best way to do things is to burrow a hole keep going in one spot until you get a hole, and then you get a lot of points for free, essentially. You don't need to do anything, and kind of mastered the game. This is kind of the game that's perfect for computers to do well at, right? Because it's tuning a very continuous control variable to hit something. So in hindsight, it's not that hard to imagine. So yeah, that one was called Breakout. That game that we were looking at. And so here's a graph of all the games that they played in the Atari dataset. And here's the performance as a measure of human performance, right? And so 100% is you can do as well as human beings who are good at this. And this was the line of, on the first set of things, that on all these games they were better than human beings at it. And they used the same algorithm to learn on all these games, right? So they would retrain it on different games, but they didn't have to change anything specific to these. So it was a big deal because usually the reinforcement learning algorithms before this were not that flexible. But since the model is so flexible, you can use it to learn many different types of things. And the types of games you're learning here often have that same kind of feel, that it's moving a small controller that is shooting or gets out of the way or something. And the ones where it did badly at, and some of them it's still hard to do, are ones where you can't just see what to do directly from the image because it's hidden away somewhere, right? So you have to go find the key, which opens the door, which helps you save the prince and get the money or something. And if that's not visible in the image, then there's no way for the neural network to learn that, right? So it's not magic, but it is very powerful. And so then they try to visualize, some people try to visualize the state space of the DQNs and kind of cluster together all of the states for different encodings. Like I said, when every board game state has an encoding in the network. So once you basically give it this and the action you took, it'll give you a particular vector of numbers that represents all the weights, well, not the weights, the activations for every one of those weights inside the network. And so it's basically a signature of this state, right? And you could use the distance between those to map them out and say, well, they're similar and the numbers are exactly the same, they must be the same board. If they're off by just a couple bits, they're actually probably pretty similar. And so you can map out neighborhoods of boards in essentially somehow the mind of the game, of the agent, that, there are types of boards where, there's only one alien left or many aliens, but they're all on the right. And so it has a certain strategy. So it's really learning something. It's very exciting. As they're trying to figure out how this worked and why it worked, it is learning kind of shapes and representations. So some of the researchers were saying that it's like learning that a pixel beside this other pixel is bad or good, but it did have the ability to abstract those because it's all about local relationships. It's not about memorizing exact pixels. So that's how this one worked, right? And this was, like I said, 2015, and it really kicked off a flurry of all these other things. None of this existed before that. If I go in order of how I remember it happening, there was these ones, and then this one, and this is later, this is new. I guess this feels like almost the same. This is the hindsight experience replay, so going back and using that memory to learn better. This one's very exciting now, as is this one. So we're going to talk about these two and then some other videos, but there's lots more, and there's other ones that are not here that haven't been added, so maybe we can go and fill in the table. But it's been expanding since, but this main idea of DQN is kind of the start of it.